Hello everybody, and welcome back to another geometry video. Today we're going to take a look at section 11.3, which is all about area of polygons. Now, we've done a bit with area already. We know what the area of a triangle is, and we know what the area of a square is, and recently, as of today, last class, we know what the area of a circle is as well. But what we are going to be trying to do is we are going to try to see if we can find the area for any polygon. Doesn't matter what type it is, whether it has 5 sides, 10 sides, 20 sides, whatever may have you. Before we jump into that, I want to talk about how we can find the area of shapes that don't have a formula. These shapes are called composite shapes. Composite shapes are what you get when you put multiple shapes together. So this shape, for instance, doesn't have a name, but we can very clearly see that it is made of a square on this side and 1/2 of a circle on this side. So how do we find the area of a composite shape? Well, since it's just made up of these two shapes, we could find the areas of both of them and add them together. So the area of this shape, the entire thing, is going to be the area of our square plus the area of this semicircle. That's the area of the square, that's the area of the semicircle. We just have to find both of those and we'll get the area of the entire thing. Now, one of these areas is easier to do than the other. The area of a square, we know, is just base times height. In this case, the base is 22, the height is 22, that's what makes it a square. So the area of the square is just base times height, or 22 times 22. When we plug that into our calculator, we end up getting 484. So 484 is part of our area here. It's going to be 484 plus something. Now, the area of a semicircle is not something that we've learned how to do, but we can infer how to do it. After all, a semicircle is just going to be the area of a full circle cut in half. So we have to find the area of this shape if it was a full circle. Imagine if it was going all the way around like this. Well, the thing that we need to find the area of a circle is the radius. After all, the formula for the area of a circle is pi r squared. So what's the radius here? Well, since the entire length here, the diameter, is 22, we know our radius is half of that, so 11. That means our area is going to be pi times 11 squared divided by 2. If I wanted to simplify this out, 11 squared is 121, so this would be 121 pi divided by 2. So to find the composite shapes area, we just add 484, the area of the square, plus 121 pi over 2, which is the semicircle. Let's calculate this out and see what it is exactly. So 484 plus fraction 121 pi over 2 gives us 684.07. So the area in total is going to be approximately 674.07. And since we're talking about area, remember, our units for area are always squared. So if we're doing all of our measurements in feet, the area will be in feet squared. I want you to try and pause the video and see if you can find the area of B here. Break it up into shapes that make sense for you to find the area. Let's pause here and give it a shot. Hopefully you've given this a shot so far. There's a lot of different ways to do this problem. But the way I see it, I see 4 different triangles here. But wait, those aren't 4 different triangles. All these triangles are the same. So the area here is going to be 4 times the area of just one of these triangles. Let's figure out how to find the area of the triangle. So the area of one of these triangles is going to be 1/2 base times height. That's our area formula. If I'm taking a look at just this one here, the one that I've outlined, we know that the height is going to be this little segment here, and the length is going to be, or the base is going to be this segment here, because it's a right triangle. Since the entire measurement of this side is 10, that means the height is 5. Since the entire measurement here is 24, it means the base is 12. So 1/2 of 12 times 5 is going to be 30. So since our area is 4 times that, we get 120 millimeters squared. Again, you could have done this many different ways. This is just how I did it. Now, what shape is this that we have just found the area of? Like I said, this shape over here doesn't really have a name, but this one absolutely does. What do we call a quadrilateral that has 4 congruent sides? This here is a rhombus, folks. So what we've done is we've actually found the area of a rhombus by splitting it up. You can always try this out. If you can split up a polygon into a bunch of smaller shapes, you can usually find the area. We're going to do that a little bit later today, but here's what I'm wondering. Is there a way we could use this to make a new formula? Let's look at this rhombus here and see. We have a side length of 24, a height of 10, and it ends up equaling 120. So here's my question for you to ponder. How do the numbers 24, sorry, this marker just died, 24, 10, and 120 interact? What could we do with the numbers 24 and 10 to get to 120? Can't be adding them. Adding will give us 34. Subtracting gives us 14. It's not even close. But what happens if we multiply 24 and 10? Well, 24 times 10 would give us 240. That's double 120, right? Okay, so what? So what this means is we've already discovered a theory for how to find the area of a rhombus. Take these two measurements here, multiply them together, and cut them in half. You'll get the area. Believe it or not, this is how people have found the area of a rhombus formula. But there's some specifics about this. The area of a rhombus is 1/2, since again we multiplied these and cut it in half, of this side times this side. And we need to give these sides names. We can't necessarily give this the height treatment because it has a more specific name. This 10 millimeters is not just a height, it's one of the diagonals of a rhombus. So I want to say the area is 1/2 diagonal 1 times diagonal 2, where D is a diagonal. There we go. That's it. That's the area of any rhombus and any kite. As an example, if I give you the following shape, let's say I've got one that looks something like this. This is a kite. If these two sides are congruent and these two sides are congruent, it's a kite. If I know the lengths of my diagonals, if I know that the length from top to bottom diagonal is, I don't know, let's call it 6, and the length from the diagonal going across the shape is, let's call it 12, the area will be 1/2 6 times 12. Half of 6 is 3 times 12 gives us 36. This is how we can use an area formula. All right. This next part is going to be a bit tricky. Before we jump into any definitions here, I want to mention that we are going to be using all of this space in our examples for all of these definitions here. I'm going to do this on a separate sheet of paper so that it's actually legible. Here's what I want you to do in your example spaces. I want you to draw, as best you can, a pentagon. Pause the video and draw one now. Something like this is what we should end up with, a pentagon. Now, I want you to find, as best you can, the center of this pentagon. I happen to have a compass here with me, which is going to help me find that center, but it should be around right here, I think. Let me just do a quick couple measurements here. Yeah, it looks like the center of our pentagon is going to be right about there. No, it's a little off. Let's call it right here. From the center of your pentagon, I want you to draw a circle that circumscribes this pentagon. My circle is not going to be perfect because, unfortunately, I did not find the perfect center. I really should have found the center before I did this. But we draw a circle around it. Now, there's a couple of things about this shape that I want us to identify. First off, we have two shapes here, a circle around the outside and a pentagon on the inside. But both of them have this point as our center. The first thing I want you to identify is the fact that the center and the radius of a regular polygon equals the center and radius of its circumscribed circle. Basically, if you can put a polygon into a circle like this, the center of the circle is the center of your polygon. And most importantly, the radius of your circle, if I was to draw a line connecting the edge of my circle to the center of the circle, that radius is also going to be the radius of your polygon. So when we say the radius of a polygon, we mean from center to vertex. Cool. As we look at this shape, we learned that we can split up shapes into many smaller shapes to help us find the area. I see a couple of ways we could do this, but the one that we're going to go with today is this. Draw a bunch of radii going out from the center of your circle to each and every one of the vertices of your pentagon. Again, this would look a lot nicer if I had an exact center, but it's okay, we get the point. And let's call all of these R, because, I mean, they're all radii, they all should be the same length. If I could find the area of any one of these triangles, I would be absolutely golden. The reason is the area of this pentagon could just equal 5 times the area of one of the triangles, since there are 5 triangles around. And we know that that's just going to be 5 times 1/2 base times height. We've got some problems with this, though. The problem is we know neither the base nor the height of these triangles. On top of that, we don't even really have a height drawn. Before we do so, I want to give some measurements to these radii. These aren't going to be exact measurements, but I'm just going to call them 5. 5 what? That's up to your imagination. But let's say all the radii of this shape were 5. Our goal is going to be to find the measurement for the base of one of these triangles. Since this one's the nicest one, I will rotate my page. We have to find the base of the triangle, B, and we have to find the height of this triangle. The height is always going to make a right angle with the base. If we can find those two things, we will be so golden. We will have our area. It's time for a quick little definition here, folks. That height that we just drew isn't just a height. It's a line that goes from the center and is perpendicular with one of the edges. We have a special name for a side that's drawn like that, and we call it the apothegm or apothegm. Both are correct pronunciations. The apothegm of a regular polygon is the distance from any side of a regular polygon to its center. Think of the apothegm as the height of a triangle that's inside of a regular polygon. So the apothegm is what we are going to be calling this. I'm going to give it the letter A. Finding the apothegm is really tough, though, because we only have a couple pieces of information that can help us. The first thing we might notice is we do have a right triangle here. So if we knew 2 of the sides, we could use the Pythagorean theorem, for instance. We don't know 2 of the sides. If we knew an angle in this triangle that's right here, this right triangle, we could use our trigonometry. We don't have an angle. But this second part we can actually do something about. We can actually make an angle. Folks, if we took all points of all 5 of these triangles in the center and combined them, bam, 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 what shape does that make? All 5 angles would come together and make a circle, right? So we know that the sum of these central angles is 360. The sum of central angles is 360 degrees. And wait, aren't there 5 triangles here? If you want to find the measure of a central angle, we can just take 360 and divide by however many triangles we have on the inside. In this case, there are 5 big red triangles. In the future, we're not actually going to draw these triangles out. That'll take too much time. So just know the number of triangles you end up with is going to equal the number of sides of your polygon. This is a pentagon, so there are 5 sides. So all we need to do is to do 360 divided by 5, and we get that the central angles here are all 72 degrees. 72, 72, 72. The only thing is, we don't want the entire angle for our right triangle. We only need this angle that I've given 3 tick marks to. But the good news is, this is an isosceles triangle, because both sides are 5, that we have just cut down the middle. So both halves of this angle are going to be the same. If the entire angle here is 72, then this half of the angle is 36. We have a right triangle that has an angle and a side. Allow me to redraw this below so we can take a look. We have a right triangle that looks like this. We want to find A, our apothem, and we have the radius is 5, and this angle is 36 degrees. Since it is a right triangle, we get to use right triangle trigonometry: sine, cosine, and tangent. So if you recall, sine is used when we're trying to find the opposite or hypotenuse. Cosine is used when we're trying to find the opposite or adjacent, or the opposite or hypotenuse. Messed up the abbreviation. Tangent is when we're trying to find the opposite or adjacent. So in this problem, what information are we using from this angle here? We don't have the opposite side. The adjacent side is A, our apothem, and our hypotenuse is 5. So we can use cosine. To solve for A, the cosine of 36 would equal adjacent over hypotenuse, so ka toa. So sorry folks. Adjacent is A, our hypotenuse is 5. Since cosine is adjacent over hypotenuse, our adjacent is A, our hypotenuse is 5. So what's the thing we have to do to solve for A? Since this is A divided by 5, we just have to multiply by 5 on both sides. We now have the length of our apothem. Our apothem is whatever 5 times the cosine of 36 is. Nice! That's one piece to our puzzle. Our apothem, I mean, we could calculate this out as a decimal, but I don't want to round anything just yet, is 5 cosine of 36 degrees. Lovely. What we've just found is the height part of our area formula. There's only one thing left that we need to find, and that's the base. The base of one of these triangles seems to be 2 little segments that you could make with the right triangles. What we're really trying to find is this. I'm going to call it x. So let's go back down to our right triangle. If I'm trying to solve for x, what should I do? Well, we have our 36-degree angle. X is opposite to it this time, and our hypotenuse is 5. Can't we just use the sine of 36? Because sine is opposite over hypotenuse. The opposite is x. The hypotenuse is 5. All we have to do to solve this is just, once again, multiply by 5. X equals 5 times the sine of 36. That's this part of the side, this half. But just remember, if this is 5 sine of 36, we want the entire side, which is double that. So what's 2 times 5 sine of 36? 10 sine of 36. We have now found the missing pieces. We found our height, which we call the apothem, and we found our base, which is just a side of the pentagon. The area of this pentagon, then, can be given by this. 5 times 1/2 Our base, again, was the side of the pentagon that we found. It was 10 sine of 36. And the height, our apothem, was 5 cosine of 36. Let's plug this all into our calculator and see if we can find the area of our pentagon. Since there are 5 triangles, we multiply 5 times our triangle formula. Our triangle formula is 1/2 the base times the height. Our base was 10 sine of 36 times our height, which was 5 cosine of 36. We should be good to go. The area of this pentagon is 59.44. So that is how we find the area. But that seemed like a very long process. It is. It is a long process. You're not deluded in thinking that. Which is why I'm going to try and shorten it as much as possible. It won't be short, but it will be shortened. Let's start by getting these definitions in, and then I will give you the formula we can use that'll make things a little easier. First things first, the central angle of a regular polygon. That's when we found the central angle here. It's all of these angles. So one central angle of a regular polygon is going to be essentially just the angle formed by 2 radii of the polygon. And to find the measure of this central angle, we just had to do 360 divided by the number of sides. Now it's time for the big reveal. This formula we used, this 5 times 1/2 base times height, can actually be shortened a little bit. Let's reorganize some of the terms. 5 times, let's reorganize it like this. 1/2 times, instead of height, we're going to use the letter A, meaning the apothem. And instead of a base, we're going to use the letter S to represent the side of a polygon. I know 5 and S look similar. But wait a second. If S, or we used here was B, is just one of the sides of the polygon, and there were 5 total sides, what do we call 5 times S? It'd be the distance around the outside of our polygon, which we know as the perimeter. So this can be shortened to 1/2 A times the perimeter. This is our shortened formula. The formula for the area of a regular polygon can be written as A equals 1/2 A times P, where A is the apothem and P is the perimeter. But if you don't like this formula, we can also just write it the way that we sort of solved it together. 1/2 A times the number of sides times the side length, where N is the number of sides and S is the side length. That is the formula. Let's take a look and see if we can practically use this formula. Before we do anything, I need us to practice finding the measure of those central angles because, if you recall, the only way we were even able to solve this right triangle was because of this 36-degree angle. It showed up everywhere in our calculations. So let's talk about how to find the central angle. If we're trying to find angle AFB, that's this angle right here, That's a central angle of the polygon, because these two sides are both radii that stretch to the corners, to the vertices. So to find the measure of a central angle, just do 360 divided by n, where n is the number of sides. It's still a pentagon, so it'll be 5, and wouldn't you know it, the central angle is still going to be 72 degrees. So, once we have that, we've got our central angle. Perfect. What about the measure of AFG? AFG is just this inside angle, which is half of the central angle. So take the measure of angle AFB and cut it in half, and we will get the measure of this one. This is the angle that we're going to be using when we're actually doing our calculations. It's this angle, half of the central one. And if you really wanted to, you could also find the measure of GAF, this blue angle I've just highlighted. It's kind of hard to see, but it's the angle on the side here. But we know that the top angle was 36, and this is a right angle, so we're just completing the triangle. We're seeing what adds to make 180. GAF will be 180 minus our 36 degree angle minus our 90 degree angle. That's just going to be 54 degrees. Cool. Now, let's actually use what we have learned. Over here, I give you 4 problems, which is a lot. But genuinely, I mean it, and I believe this when I say it. The more you practice this skill, the quicker you will get at it. So, what I'm going to do is, I'm going to do example A and example C. I want you to try B and D and then check in with me and see if you got the same answer. Let's take a look at example A. Example A asks us to find the area of the regular polygon. Our grand formula is going to be area equals 1/2 A times P, the perimeter. So we need to find the apothem. And to find the perimeter, we need to know all these side lengths all around the hexagon. So let's begin where we always do. In order to make this right triangle solvable, let's first label it. Our diameter of this shape is 32. The diameter of the hexagon is the same as the diameter of the circle. So our radius here, this side of the triangle, is 16, because it's half of that. But we need to find A, this length over here, our apothem, and X, which is just half of the entire side length. What we've basically got is a right triangle that looks like this, where we know that this hypotenuse is 16, we know that our apothem is A, and we know that our half of the side length is X. In order to solve this, though, we need an angle. And what better angle to make than a central angle? So here's what I'm going to do. I'm going to draw out a second triangle over here, and I'm going to find this angle. The reason is, if I can find this angle, the angle on top of our little right triangle here will be half of that. So how do we find the measure of the central angle? Well, a central angle equals 360 divided by the number of sides. In this case, the shape is a hexagon, so it'll be 6 sides. 360 divided by 6 is 60 degrees. So if our central angle is 60 degrees, what's the measure of this angle? It's 30 degrees. This presents us with something very interesting. if we have a 30-degree angle and it's a right triangle, isn't this a special right triangle? Folks, this is a 30, 60, 90 right triangle. Now, we could do all the trigonometry that we solved our first pentagon with, all of this, but I'm going to be honest. If you remember your 30, 60, 90 right triangles, this is a great, great shortcut. As a reminder, in a 30, 60, 90 right triangle, if this side is x, the short side, the hypotenuse is 2x, and the long leg is x root 3. So in our triangle here, the short side is x, our hypotenuse is 2x, but it's written as 16. If 2x is 16, what is x? X is 8. And if x is 8, and we know that our long leg here, in this case our apothem, is a long leg, according to our special right triangles, that long leg should be x root 3. If x is 8, our apothem is 8 root 3. Okay, we've actually got most of our information here already. But keep in mind, we need the apothem and we need the perimeter. This little x here ends up being 8. So what's the length of an entire side? Well, it's 2 copies of 8. It's 16. So that side's 16, this side's 16, this side's 16, this side's 16, this side's 16, and this side is 16. So the perimeter is just going to be 16 times 6. 6 of them. Let's calculate that perimeter. Our perimeter, 16 times 6, is 96. And our apothem is 8 root 3. So we have everything we need. 1/2. Our apothem, our a value, was 8 root 3. And our perimeter, we found, was 96. So the entire area for this big shape here is just going to be 1/2 of 8 root 3 times 96. If we plug that all into our calculator, 1/2 of 8 root 3 times 96, 665.11 is our area. 665.11, but we can't forget, what units are we dealing with? In this case, we get off sort of scot-free. We aren't actually given the type of units that we're dealing with. So we can just say units squared. There's our answer. It's basically just trigonometry and then throwing it into a formula. Cool. Part C looks a little bit different. For part C, we have a lot more sides, but notice that we're also no longer given the radius here. Instead, we are given the side length. So what we have in this problem is we actually have an easy way of finding the perimeter, but a tricky time finding the apothem. Let's start off by finding the perimeter, since that's part of our formula. Sorry. If one side of this regular polygon is 6, and again it says it's a regular polygon, that means all of the sides are just 6. So this is 6, this is 6, another one, another one, another one, another one, another one, and another one. How many 6s do we have here? Well, there's 9 sides here, actually. So that's where the formula a equals 1/2 a times ns could come in handy. We know the number of sides is 9. We know that the side length is 6. We could just multiply these two together. N times s is 9 times 6. which, as we know, is going to be 54. So our area is 1/2 A times 54. That's our perimeter. That's why these two are the exact same thing. You can use whichever one is more convenient for you. But what we need to find now is the apothem, and there's nothing drawn here that makes the apothem. So we've got to do it ourselves. Putting you guys to work. To make the apothem, remember that we're eventually going to need a right triangle here. Our apothem is the height of the right triangle. So what we basically got is a very skinny looking right triangle with height A. We do not know the radius here, but we do know the bottom of this triangle. If the entire base of the nonagon is 6 inches, the base of half of it is 3 inches. All we need in order to solve for A is this missing angle right up here. So how do we find it? Well, recall that we can find the central angle of a triangle of one of these polygons, then cut it in half. So let's find the central angle. The central angle is going to be 360 divided by, since there are 9 sides, it'll be divided by 9. 360 divided by 9 is actually going to be a very nice and even 40 degrees. So the measure of this central angle is 40. But we only need half of it for our right triangle. So instead of using 40, we are going to use 20 degrees. Again, to find this A value, we have to use trigonometry. So let's look at this angle and see what information we know. We know the angle. We know the opposite side is 3, and the adjacent side is A. Opposite over adjacent is just tangent. So we can say the tangent of 30 equals opposite is 3 over adjacent, which is A. To solve this, then, we just have to be a little creative. We want the A out of our denominator, so let's multiply by A on both sides to get A times the tangent of 30 equals 3. All we have to do now to get A by itself is divide by the tangent of 30. Divide by the tangent of 30 on both sides, and we get A equals 3 over tan 30. That's it. We have the last thing we need to plug in. So our whole formula, if I zoom back out a little bit, our whole formula was 1/2 A times our perimeter. Our perimeter was 54. So our area equals 1/2. Our A is 3 over tan of 30. And our perimeter was 54. So we just have to multiply all of these out. Once again, we'll use our trusty calculator here. We will get 1/2 of 3 over tangent of 30 to multiply 54. We get our answer. The area of this nonagon is 140.3. This time we have a unit, inches. So remember that area is always squared. So inches squared. I'd like you to pause the video and see if you can tackle B and D. They're the exact same solving methods, but with different numbers and different shapes. Pause the video and give it a shot. How do we do? I've written down my processes for both of these problems, but if you do have troubles reading them or understanding the flow of them, let me know. I'm happy to show you. The idea for both of them is, though, you've got to find that apothem somehow. In this problem, since our central angle was 40, this angle here was 20, it was 4 cosine of 20. We also used the perimeter, which is 8 sine of 20 times 9. This problem over here, the apothem was the only thing we needed to find, and we could use half the side length of 7 as the base of our triangle. Cool. Last, most certainly not least, we have example 3. And example 3 is a bit of a weird one. It's not going to add much more to the problem, but yet, every year, I find that students tend to stress out about this one. I think this is a pretty easy problem, just because we're adding only one step, and we only do that one step at the very end of the problem. You'll notice that I am shading this area here. I'm sort of coloring it in with these black lines, because this problem isn't asking for the area of the pentagon. It's telling us that we have a circumscribed pentagon here. It's a pentagon that is inside of the circle. And our task is actually going to be to find this shaded area. So how do we even start thinking about that? Well, the shaded area is part of a circle, right? It's just the part of the circle that the pentagon is not in. So all we need to do to find this shaded area is find the area of the entire circle, then subtract the area of the white space inside of it, the area of the pentagon. Sounds easy-ish. Let's see what we can do. To find the area of a circle, we really need a radius, and we don't have a radius here. So our first goal is going to be to find the radius of this shape. Afterwards, the area of the pentagon is 1/2 our apothem times our perimeter. And hey, the perimeter actually seems pretty easy to find. I mean, after all, we know that one of these sides is 12. So if that side is 12, then this side is 12, and this side is 12, and this side is 12, and this side is 12. The perimeter of the shape is just 5 times 12, or 60. So we know that our perimeter is actually just going to be 60. We still need the 1/2 times A, and we still need our radius. So let's tackle those. To find our apothem, and to find our radius, really, we need to make a right triangle somewhere. I think this will be a perfect one. So we have a right triangle. Our radius r is going to be this length. Our apothem A is this length. And we know that the side length here is 1/2 of 12, because we cut it in half to make the right triangle. So this is 6. The only piece we need is this angle up here. And well, to find that, we just take the central angle and divide it by 2. The central angle of this polygon is going to be 360 divided by 5, because there are 5 sides. 360 divided by 5 is, hey, 72. We already sort of dealt with that angle before. And we know that 1/2 of 72 is 36. So our degree of our angle here is 36 degrees. Let's find an expression that we could use to represent A. A, our apothem, is the adjacent side. And since we know the opposite side is 6, tangent is what we will use. The tangent of 36 equals opposite, which is 6, over adjacent, which is A. If you remember a shortcut that I showed you earlier on in the year, remember that we can always swap the position of a denominator with the entire other side of an equation. In other words, we can write that our expression for A is 6 over the tangent of 36. If you wanted to, you could just multiply both sides by a and divide by tangent of 36. You'll get the same thing. What about our radius, r? Well, r is the hypotenuse of the shape. So I'm going to look at this as a sine problem, because the sine of 36 is going to be the opposite, which is 6, over the hypotenuse, which is r. Again, we can use our quick switcheroo technique to say that r is just 6 divided by the sine of 36. We've just found the only two missing pieces in our equation. We found that our radius is 6 over the sine of 36. Just don't forget that it's squared according to our formula. And our apothem ended up being 6 over the tangent of 36. So this long chain of numbers is our formula for the area of the shaded region. It's the area outside of the pentagon. Let's do some calculating. You could do this in pieces, but I personally love seeing a problem like this come together. I mean, it's such a long formula we've put so much time and effort into, and we can just plug it all in and finish the problem all in one go. So pi times our radius, 6 over sine of 36 squared, minus 1/2 of 6 over the tangent of 36 times our perimeter of 60 gives us 79.60. The area of the shaded region here is 79.60. Done and dusted. Units squared. Very nice. With that said, folks, that concludes our notes for tonight. Thank you so much for listening, and I hope you have a fantastic rest of your day. Take care.